In this video, what we're going to be looking at is averages, because when you do experiments, you do multiple trials. In doing multiple trials, of course, it makes your data that you collect more reliable. So you don't just do an experiment once and go, yep, I've got it. You repeat it because you want to try and minimize errors and come up with reliable trends. And that's what trials are all about. Okay, and so in this experiment here, I don't know if you've seen them before, these devices, air cannons they're called, or air zookers. Now I've got some, but it's pretty hard to show you here, but I'm going to pop some pictures up and some video up of air zookers. They're pretty cool devices. When you pull them back and let go, a bit of elastic in some plastic at one end pushes the air out, and that pulse of air travels a distance and hits an object. Sometimes the objects can be curtains, sometimes they can be cups, sometimes they can be people's hair. A bigger version, of course, is the one that I like to do, is using bins. You can use a bin, cut out the hole, and you can make vortex rings. Here's some videos of me doing those and some pictures. They're pretty cool, a lot of fun. So in this experiment here, a student was standing from a doorway, and that doorway had some curtains, and those curtains could move backwards and forwards, and they were standing with their air zooker. Okay, so there's their air zooker, right? And they pull the plastic back, and when they pull the plastic back and let the plastic go, a pulse of air comes out, travels a certain distance, and when that pulse of air hits, the curtains move. And what they did is they wanted to see if there was a relationship between the time it takes for the air to travel and the distance that they were standing away from the curtain. So there's the distance, and they were going to be measuring the time. And this is what they got. They stood at 6 meters away, they pulled back, they let go, and they noticed it took 0.37 seconds for the curtains to move. So they recorded it, and then they repeated it. Then they moved to 10 meters and they did multiple trials, 14 meters and 18 meters. And then, of course, they have to graph it. Now, to graph it, you're going to be graphing the average. You're not going to be graphing every single trial, because we need to make sure we have nice one line. So let's work out how we graph this. And I'm just going to rub this out so I'm not looking through the arrows here, right? So let's get rid of this. Okay, so we said that our acronym was TAILS. So we need a title, but before we can do a title, we have to work out our variables. And remember, our variables are the things that we are changing and we're recording. So what we record is the dependent variable. And according to the axes with dry mix, the dependent variable goes on the y-axis. There it is. The independent variable goes on the x. Okay. So what we're changing here goes down the bottom. All right. Remember, like a baby sitting down, you change the bottom. You put the nappy on the bottom. So what you're changing goes down on the bottom of the grid. So what are we changing here? We're changing the distance. So the distance is the independent variable. It's the one that's being manipulated. We're changing it. So we've got the distance here. And we need to put the units, which is meters. Okay, so we've got our axes and we've got our labels and we've got our units. So now let's do the dependent variable. The dependent is what we're measuring. We are measuring the time, and the units are seconds. So here's a bit different because, see, a lot of graphs, students think time always goes down on the x-axis. No, it doesn't. We want to make sure that the dependent variable is on the y and the independent is on the x. And in this case, time is a dependent variable, right? That's what we're measuring. So now we've got that sorted. We need, of course, to come up with some values here. But before we can come up with some values, we need to calculate an average, because we want to plot the average time versus the distance. So how do you do averages? Well, depending on how old you are and how much maths you've done, an average is just summing all these together and then dividing it by the total, right? So we'll just do one. So the average time for at 6 meters is all these times. So 0.37 plus 0.45 plus 0.48 plus 0.33 plus 0.29 plus 0.42. All of that over how many we have? 1, 2, 3, 4, 5, 6. So when you add all those up and you divide the answer by 6, the time that you should get is 0.4. Okay, and we're going to put the averages of the others in. So you should get 0.7. Okay, so there are the averages of all the data. Let's just rub this bit out. Okay, so now we have to work out our axes, right? We have to work out the intervals, I should say. The I stands for interval. And remember, the intervals should represent the same amount. So let's have a look at our data here. Let's do distance first. So we're going from 6 to 18. So let's just round it off and make it 20 maybe. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, and then of course 20 would be there. So 2 works well. 2, 4, 6, 8, 10. All right, so that stretches that across. I mean, when we said scale, it had to be over 75%. Well, that's going to make that happen. Let's have a look at our other variable here, our dependent. We need to go up to 2.3, so let's round it to 2.5. And so let's see how we go. So if we go 0.2, 4, 6, 8, 10, which is 1, 1.2, 1.4, 1.6, 1.8, 2, we're going to run out of space here. Okay, we'd have to go to 2.5, which is up here. So we need to think of, try and make that 2.4 there. So we started from 0 down here. What's our lowest value? 0.4. So let's start at 0.4. Okay, and then we'll go up and we'll see if we've made it now. So 0.4, 0.6, 0.8, 1.2, 1.4, 1.6, 1.8, 2, 2.4, 2.6. We've made it. Okay, so let's do that. I think I said up, I forgot a number before, but that's it there, yeah? Going up by 2, so let's double check. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, perfect. All right, so let's graph it now and see how we've gone. So at 6, we go to 0.4. So at 6 meters, we go 0.4, which is the bottom one. At 10, we go to 0.7. At 14, we go 1.19. And at 18, we go 2.34. So there we can see here that this is a curve again. It's not a straight line. So the curve goes up in between these points. So let's see if we go like this. Now that was down here, so it's going to, actually, let's have a look here. No, because all this is 0. So we could say it's a straight line there. Okay, so let's get our ruler out. Okay, so there's our graph there. That's a straight line. So that's a nice spread out graph, okay, and we can use that data. But there is, I guess you could argue, there's a problem with that graph too. The problem is because we started at 0.4, if we wanted to try and predict the time it takes at distances less than 0.4, we couldn't do it with this graph, right? We could do it with greater than 0.4, but greater than our largest distance, 2.4. So if we wanted to extend this graph out, we could predict outside that area, but we can't predict lower than that, okay? So if you wanted to do that, you would have to just adjust this scale to start from 0, 0, and then you'd have the full range of values from which you could what's called extrapolate, and we're going to be talking about extrapolation in another video. But let's just keep this one here for the moment. And so we've just worked out our averages. That's the skill we're looking at, taking averages and then plotting it on a line graph. So hopefully that makes sense, and we'll do that again in another video, I'm sure, but we're moving up and getting more and more complicated now. And I'll see you in the next video.